All right, friction fans, this one's for you. So today is all about what is friction, what's it all about, how do you make it more, how do you make it less, and how do you describe how sticky situations are. And this picture is funny because polar bears can't read. All right, here we go. So, force of friction. So it's a grab between solids. So when you have a mass moving through a fluid like air or water, we call that fluid drag, but we don't call that friction. Friction is really between two solid surfaces rubbing on each other's. So there's a little grip between the two surfaces here. They slide against each other. And some things have more friction than others. So we're going to talk about why do some things have more friction and how do you get more friction or less friction. It also depends on how they're pressed together. And it has to do with tiny bumps, but it's not really the only story. It's not just the bumps, because you can have stickiness without bumps, just like tape. An example is like a crate on the surface. So look at this. You slide in that crate and all those bumps grab each other. So that's part of the reason there's friction, but that's not the only reason that there's friction. Okay? So friction between the crate and the smooth wooden floor is less than on the rough. Now it says smooth. So it looks smooth to me in the macroscopic view, but if you get on the microscopic view, things aren't as smooth as you might think. And there's all kinds of little things to grip on, just like your fingerprints are much larger than these grooves even, but your fingerprints help you grip things as well. All right, let's keep on rolling. So it's not all bad because you didn't have friction. There's a lot of things that couldn't happen. Okay, so it's a good thing. But in some cases, we try to minimize the friction. In other cases, we try to maximize the friction. Like if I want to tear down the road really fast in my car and take corners really fast, I need lots of friction so I can take them a lot faster than maybe what a normal person could. Alrighty. So what friction does, it's always opposite of motion. It resists any kind of movement. Okay? So if something's at rest, there actually is no friction whatsoever. Because if it's at rest, all forces are balanced. But when you try to push on something and it doesn't move, well, then there's friction. Okay? I'll give you some examples here in a second. So friction resists motion. It's equal to the applied force, then no motion occurs. Okay? So friction that holds an object in place is called static friction. So we're going to talk about two kinds of friction today. One being static and one being kinetic. Static has to do with things not moving, like static electricity. Your hair might stand up because charges aren't moving. They're sticking in your hair and your body, and they're not moving. That's what static means. Right now, you're likely to be static and not moving if you're actually looking at this video. So this is what we're talking about is static friction. So for instance, if this box is just sitting there, all forces are balanced, gravity pulls down, the surface pushes straight up, there aren't any sideways forces on it. Since there are no sideways forces on it, there's not any friction. But if you go at an angle, gravity's not straight down, or gravity's straight towards the ground. But we have a component in this direction. And since you have a component of gravity this way, the only thing keeping this thing from sliding down the ramp is friction in the other direction. And it has to be the same amount if the box doesn't move. Or if it's moving at a constant speed down the ramp, these two forces would have to be equal, the gravity and the friction. We'll see those situations later on. Okay? Alrighty, so a couple things. Here's kind of a misconception. A lot of people think, hey, greater surface area is more friction. In most cases, no, that's not true. Surface area is usually not a big factor. Not in every case, but in most cases, no. So we'll find out that friction does vary with the mass of the object, because the more the mass, the harder gravity pulls on it. This pulls it into the surface harder, meaning it grips better. But friction is actually independent of the surface area. Por ejemplo, these two things are the same weight. Okay, this is toppled over on its side, and this is standing up on the side. So it's the same weight or force shoving this into the surface, same force shoving into the surface here. The difference is this force is more spread out. You might think, hey, there's more grip. Well, not really, because there's less force per area. Because you have a greater area, the force is all spread out, so you really don't get any better grip. So we're looking at a microscopic picture of what's actually in contact, because you have the same weight or force on a smaller area, you can dig into the surface a little better. And you actually have about the same points of contact in both cases, even though you have a greater area. Because you're spreading out those points of contact, as here you're more concentrated, but you're really getting the same grip. So here we have a greater pressure, it's the same force but smaller area. Think of even if you had it down to a point. If you had it down to a point, that point might stick into the surface pretty easily because it's got the same weight, but a small area makes a high pressure and it sticks into the surface better. So because of that, for the most part, your width of your object does not affect how much grab you have. The only difference might be with some high-performance automobile tires, like your race car tires. Your race car tires, they get them hot. Maybe you've seen them in some races before, but it's important that those tires get hot and sticky. It's a different kind of rubber than what you have on your car tires, because your car tires are made to last for 40 to 60,000 miles, where your race car tires don't last very long at all because they get very hot, but they're very, very sticky when they get them that hot. So in a sticky case, when you get them hot, you can get a little more grip. But for the most part, if you're not changing the surface type by just tipping something over, surface area is really not a big factor whatsoever. Okay? Weight is, but not the surface area. Alrighty, so now let's talk about the kinetic friction. So that's when something's moving. If something's kinetic, like we studied kinematics, that's a study of motion. So something that's kinematic or kinetic, things moving. And so if you have something sliding against something else, like it's moving this way with this force, well, the force pushing in the opposite direction, that's the kinetic force of friction. If it's at rest, it's a static force of friction, but while moving, it's the kinetic. And here's the normal force, and here's the weight of the thing downward. Alrighty. Still, friction is always opposite of motion. But if it's sliding, it's kinetic friction. That's why the F sub K, F sub S was the static and not moving. F sub K is the kinetic. So sliding friction resists an object to motion, is not affected by the speed. Okay? Because if you're going faster, you're just bumping across the surface faster. You're not getting any better grab or any worse grab. Because in both cases, you're either going slow or fast, you're still bumping across the surface. You don't get any better or worse traction if you're bumping across the surface faster. For instance, if I were to slam on my brakes going 10 miles per hour, I get the same grip if I slam on my brakes going 20 miles per hour. I don't get any better grip by going faster or any lesser grip by going faster. It's the same grip. It is harder to go around corners going faster, because we're going to learn about that in next semester, is when you go around a corner faster, well, you need more grip otherwise, because it's a greater acceleration the faster you go around a corner. Alrighty, so here's something we're going to see in lab, or you actually already saw this in the lab by the time we're getting to here. So there's a couple ways to measure static friction. Static friction can be anything from 0 to its maximum amount. So if I were to pull, let's say, with 10 newtons, well, static friction pulls back the other way with 10 newtons on something. If I pull 20 newtons, static friction pulls backwards with 20. If I pull with 30 newtons, it pulls backwards. If I pull with 38 newtons of friction, it pulls back with 38. I try to go above 38, and all of a sudden it moves. And once you move, you actually have less stick to the surface. Static friction can be stickier. You can get a higher grip or a higher friction force than you can on when it's sliding, which is a kinetic situation. So it starts as soon as you start sliding, you lose some of your grip. Same thing on car tires. Ever watch the races and they go around corners as fast as they can? Well, as soon as they start sliding because they're going too fast around that corner, they can't regain control and they're going to ram right into the wall. Because as soon as your car starts sliding or skidding, same thing in the snow, you actually have less grip. So the idea is to keep that from happening for at least maximum grip. Alrighty, so it takes more force to start something in motion than it does to keep it in motion. That's what this is. It takes more force, maybe that 38 newtons, but it only maybe take 32 newtons to keep the thing moving along. Alrighty, so force of friction. The force of friction is found by pulling an object at a constant speed. You might say, hey, Why do I pull at a constant speed? Well, you can pull as hard as you want to. If I can pull as hard as I want to, that doesn't change the friction force backwards on the thing when it's moving, but it'll cause it to accelerate. And it's going to take some fancier math to find out what that friction force is. If you don't like fancy math, pull it at a constant speed. Remember, it doesn't matter if it's fast or slow, it has to be at a constant speed. Because at a constant speed, all forces are balanced. That's the first law scenario. So the normal force up and the weight down, they balance out. Of course, it's not accelerate up or down, but the idea is you don't accelerate left or right. Remember, friction is always opposite of motion. So as long as you were to pull this not upward, because that would make it seem lighter, or downward, make it seem heavier because you got a component going into the ground, you pull it parallel to the surface, and at a constant speed, this pulling force has to balance the friction force. Or it could be a pushing force. It's still a P force, has to balance the friction force if you're going at a constant speed. So that's how you measure friction forces. That's what you already did in lab, is you found those forces by pulling at a constant speed, not accelerating. Because then you have to find out what rate you're accelerating and do some FMUS stuff to go back and find the friction force. Much easier just to pull at a constant speed. Okay, for example, 2 kilogram mass, guys. Hey, what does this 2 kilogram mass weigh? Do you remember? I hope so. It's the FMUG thing. But we're going to find the maximum static. We're going to pull it until it budges and just starts moving. So the maximum force you get to before it starts moving, that is your maximum static friction. Okay, that's something you already did in lab. Well, there's the weight. It's 2 times 9.8, which is 19.6. We're not going up or down because the surface pushes up at 19.6 as well. Okay? And it turns out if it takes 10.6 newtons just to budget in motion, just to start it in motion, that's the maximum static friction force. What if you only pulled it with 5? It wouldn't move because that would be 5 going backwards. It has to be 5 because it's not moving. All forces are balanced. What if you pull it with 7? Well, then friction pulls back with 7 because static can be anywhere from 0 up to its maximum amount. So at 10.61 or 10.7 newtons, it would budge in motion and start moving because now we're beyond the maximum static friction and we'll break it loose. Okay? So how do you find the kinetic friction? You just keep pulling it. So to find the maximum static, you pull it to just barely starts moving, and then you're going to notice you're going to need less force to keep it moving because it's going to be less sticky. That's your maximum static. To find your kinetic, it's not a maximum minimum, it's just the amount of kinetic friction. And the way you find it, you just keep pulling it. Pull it at a constant speed, not accelerating, not slowing down, not speeding up. If you're slowing down, your pulling force is less than the friction force. Notice the normal force and weight didn't change there. But you pull hard enough to keep it moving at a constant speed, and that's how you measure your kinetic friction force. It has to be the same amount. Just like it's how you'd measure the normal force by measuring the weight of the thing. It has to be the same as the weight because it's not going up or down and there aren't any other forces involved. Alright, so here's a problem with Fluffy the Wonder Hamster moving a box of force of 11 newtons. Will the box move? Well, guys, I'm going to pause right here and we're going to go to part 2 to find out how to do the math on this problem, and in just a moment. All right, be ready for part 2.